If I'm still rambling at like 10:05, remind me that it's time to take some questions. I'll take some questions before we do the quiz, okay? Okay. So we've been working with, we just finished that chapter on radicals. And we're going to work with now the complex numbers, which is just working with a new radical, the square root of -1. That's not a real number, obviously. There's no real number such that when you square it, you get -1. And when you take the real numbers, the real number line, and you just add that one number to it, j. We call it j. In most math books, they call it I. In engineering areas, we call it j because little I is used as like a variable current in a lot of applications where complex numbers are used. So we'll be calling it j. Basically, the number j arose when somebody considered what might be the solution, to this equation. And the solution does not exist in the real numbers. So when you take the square root, this is not a real number. And so we called it something new. We called it j. When you add j to the real numbers, you get the complex numbers. And when you add j, you're not just adding j. You're adding all multiples of j. You're adding all combinations of j and real numbers. So like 3 plus j is a real number. Or -5 plus 7j is a real number. So the complex numbers are actually two-dimensional. We say they're a two-dimensional vector space over the reals. And in fact, you can visualize, we'll talk more about visualizing the complex numbers, but you take your regular real number line that we all know and love, there it is, and then we add what we call the imaginary axis, and every complex number is a point on that plane. So we're just going to work with this definition of the j being defined as the square root of -1. Get used to working with these expressions. This chapter is going to be all about how do I work with these expressions, how do I solve certain equations, what are some convenient ways to write out a complex number that lead itself to more easier calculations. So the basic new fact is this pair. They go together, right? They're equivalent. J is the square root of -1, or j squared is -1. So if I want to simplify a radical, we already know that I'm looking for two of the same factor, right? There's a couple of different ways to think of this. Let's do it the way we were doing it before, is I'll just say this is -1 times 3 times 3. I've got a pair of 3's, so I could take one out. So this is 3 times the square root of -1, and then we just call that 3j. The shorter way to think of it, which is I think what we'll all end up doing, is saying, look, I've got a negative in here, so I'm going to bring that negative out as a j. If you have a factor, if the number's negative, just pull out a j and then simplify the radical. So what should we get for the square root of -1/4? If we pull out the j, we get j times the square root of 1/4. What's the square root of 1/4?
The square root of 1 over 2.
The square root of 1 over the square root of 2, which, the square root of 1 over the square root of 4, which will give us 1/2, yeah. So 1/2 j. And the square root of -5, I mean, we're still good, we have a negative, so we're going to pull out the j. But in this case, that's all we can do. So it's just j root 5. You'll notice in the first two, like I put j at the end, like I think of the real number almost as like a coefficient on j. It's really just a matter of personal preference. I think in mathematics, like mathematicians tend to do this. I think some engineers tend to write j3 more often than 3j. So they mean the same thing. You're just multiplying. When I pulled out the j at this one, I wrote it out in front because anytime I have a factor that's being multiplied by a square root, I almost always write it out the front so it doesn't look like it's inside. And that just helps me avoid errors. We have to be a little bit careful. We have these rules for radicals that we know and love. We already know that you can't split up or combine radicals under addition and subtraction, but it was super convenient that you could combine them or split them up under multiplication. But we can, like, when we said you can just combine radicals under multiplication, that's only true if they're both positive. Sorry, that's only true if they're not both negative. So to illustrate why, I'm going to look at a couple of examples. Now, the square root of -4 squared. I'm squaring the square root of -4. I know this means that I'm going to take the square root of -4 and multiply by the square root of -4. When I square the square root of -4, when you square the square root, we know that means we should just undo the square root. It should give us -4. And we'll see that it does in this case, but I'm going to show you a potential mistake, a potential error that we can make if we're not careful. So I've got the square root of -4 times the square root of -4. I'm going to simplify each of those radicals. I'm going to plot the j, because it's a negative, and then the square root of 4 is 2. So this is 2j times 2j, or 4j squared. What's j squared equal to? -1. So we get -4, just as we suspected. Now, what if, consider this, what if I looked at this product, square root of -4 times square root of -4, and I said, oh, I know I can just combine the, multiply inside the radical and then take the root. -4 times -4 is positive 16, right? This is the square root of positive 16, which is just 4. These are not equal, right? Today's big fact, 4 is not equal to -4. So in fact, our problem with this last line is that those two things are not equal. The square root of -4 times the square root of -4 is not equal to the square root of -4 times -4. That's what this warning here says. Combining radicals under multiplication is not allowed if both of the numbers are negative. So if they're both negative, just pull out the j, like we did in the top line. Simplify each radical first. And that's good practice anyway. Pull out the j first, and then do the stuff with the radicals that have positive numbers in them. So I'm going to do that first here in part B. Root -3 times root -12. I'm just going to start by pulling out the j's. I've got j root 3 times j root 12. So j times j is j squared. And now, look, these are both positive numbers inside those radicals. So I can combine those radicals under a single radical with multiplication. So we've got root 36. J squared is equal to what? -1. And root 36 is 6, and this gives us -6. On the other hand, if I have the square root of -3 times -12, that tells me order of operation says I have to multiply first inside, right? Because there's implied grouping symbols under the radical. So we have now just root 36, which of course is positive 6. Again, today's big fact, 6 is not equal to -6. In other words, root -3 times root -12 is not equal to root -3 times -12. Okay, let's do another. Negative square root of -75. The first thing we do, pull out the j. So we have negative j root 75. And now we'll just simplify that radical the way we've been doing. We could factor 75 is 3 times 25, which is 5 times 5. So we have negative j, 3 times 5 times 5, and we got a pair of 5s we can pull out. So we have minus 5j root 3. Questions so far? Okay. Let's compute some powers of j. J to the first is naturally just j. What's j squared? -1. Great. Now j cubed, if I want to find j cubed, I'm just going to write that as j squared times j. I'm going to use my rules of exponents. J squared is -1, so that means that this just gives us negative j. J to the fourth, yes, exactly. When there's two ways we could sort of see why, I think the easiest way is that it's j squared times j squared. What about j to the fifth? J, right? Because I'm using rules of exponents. J to the fourth times j to the first. J to the fourth is 1. So that just gives us j. And j to the sixth? -1. Yeah, so j to the fourth times j squared, which is 1 times -1, or -1. We're getting, the same values, right? There's a cyclical behavior to raising j to higher and higher powers. So the distinct powers of j are j, -1, negative j, and 1, and then it just sort of keeps going. And the pattern will continue. So if I wanted to find like j to the 13th or something, rather than just do j times j times j times j, what I'd rather do is just figure out where am I in this cycle, right? This cycle is 4 long, right? By the time I get to the 4th power, I'm at 1, and then it begins again at the 5th power. So any multiple of 4 in the exponent, like j to the 4th, j to the 8th, j to the 12th, j to the 16th, those are all going to be 1. And then I just want to figure out where I'm at in the cycle. Like how many factors are left over after I pull out the j to the 4th's power. So, for example, well, let's see. If we raise j to a power that's a multiple of 4. So, for example, like j to the 20th. 20 is a multiple of 4. I know, and this is the shorthand, that will just give me 1, but we could see why. J to the 20 is 4 times 5. So this is j to the 4th raised to the 5th power, which is 1 to the 5th, or just 1. That's why any multiple of 4 in the exponent will always just give you 1. We're choosing to write this as a product, and then we can use the rules of exponents. When I raise a power to a power, that's the same as multiplying. So then we're just raising 1 to a power. So that's how we use the rules of exponents to see that any multiple of 4 is going to just give you 1. Now let's look at ones that maybe aren't multiples of 4. J to the 10th, not a multiple of 4. But I'm going to write, what's that? -1. It's going to be -1. We're going to see why we could tell it's going to be -1 right away. First of all, 4 goes in there twice, right? 4 goes into 10 twice. So this is like 4 times 2 with 2 left over. So I'm just writing 10 in that way. Taking out the multiples of 4, what's left over? Now I'm going to use rules of exponents. This is j to the 4 times 2 times j squared. So j to the 4th squared times j squared. The multiple of 4, right, we know that that's going to give me 1. So this is just equal to j squared, which is -1. The idea behind this is that the multiples of 4 don't matter, right? So we figured out how many times 4 went into it, and then we went ahead and used all of our rules of exponents and said, oh, that's equal to 1. But the upshot is I figure out how many times 4 goes into it. What's left over is the only thing that we're left with. So if I'm raising j to a power, all I need to know is like, what's the remainder of that power when I divide it by 4? So if I want to find j to the 531, the first thing I'm going to do is a little bit of division. Four goes into 13 3 times, that's 12. 4 goes into 11 twice, it's 8. So it's 8 with a remainder of 3. Or not 8 with, so it's 132. It goes in 132 times with a remainder of 3. The fact that it goes in 132 times is not that important to me. It's what's left over that is important. When I divide 132 by 4, I get a remainder of 3. That means that j to the 531 is j cubed. And that's negative j. If I want to see it out sort of the long way, there it is. In the beginning, when I was talking about how we could kind of visualize the complex numbers, and I said, we take the reals and then we add j, and that means that we're not just adding j, we're adding all multiples of j and like combinations of a real and an imaginary part, like 1 plus j, or like, negative 7 plus 12j or something like that. And every complex number is like a point on this plane. In that way, we could see like the real part and the imaginary part, the j part, as being like coordinates, right? And when we write a complex number in that way, we call it the rectangular form of the complex number. So when we write it in the form a plus bj, that's the rectangular form. A is called the real part. B is called the imaginary part. B itself is a real number because it's just a multiple of j, right? But it's the imaginary part. I hate like calling these imaginary numbers. I don't hate it. Like, I'm being dramatic, but they're not like they were called imaginary. When somebody I don't know who it was, but when these were first being sort of discovered and the theory developed, like all the other mathematicians like just laughed at that guy and were like, those aren't real. Like, have fun with your imaginary numbers. Like, what do you... And to be fair, there were no applications of complex numbers until probably, 100 years later or so. It's, the backbone of, like, alternating current is, like, you have to do a lot of stuff with complex numbers. So anyway, I digress. B is called the imaginary part. A is called the real part. And this is probably not surprising. The complex numbers a plus bj and x plus yj are equal if and only if their real parts are equal and their imaginary parts are equul. Visualizing that on the plane is like, you only get the same complex number if it's the same point in the plane, right? You have to have the same coordinates. So if I wanted to do something like solve for a and b, that's actually pretty easy here, right? If a plus bj is 3 minus 4j, the only way that happens is if the real parts are the same, which tells us that a is equal to 3, and the imaginary parts are the same. And that imaginary part is negative 4. So here's one that just is slightly more involved. We want to solve for x and y. So all I'm going to do first is just rewrite this. And the left side I'm going to rewrite as 4 minus x minus 6j. Now these parentheses aren't necessary, but I think they will be helpful. So I'm going to put parentheses around the 4 minus x. In that way I could see 4 minus x as the real part. On the other side, I don't have any real part. They both have a j. So this is 0 plus, and then what is my coefficient on j on the right side? like this is the same as j times what?
1 plus 1.
Yeah, we're just factoring out the j. So now I can compare the real and imaginary parts again. So 4 minus x has to be 0, which means that x is 4. And the imaginary part, 1 plus y, has to equal negative 6, which means that y is negative 7. When we were working with radicals just the other day, and we did a problem like, this is going to be a little tangent, right? So we did a problem like, what is 1 over root 2 plus root 3? What did we do? Like, how do we do that division?
Multiply by the conjugate.
Multiply by the conjugate, and what's the conjugate?
Square root of 2 minus square root of 3.
Yeah, we just changed that operation. So right, this was the conjugate of root 2 plus root 3. Now j is just the square root of negative 1, right? The j is, we can think of j as a radical itself. So the complex conjugate of a number is, complex conjugate of a plus bj is a minus bj. Now here's what we have to be careful of. With radicals, like with the radicals from the last chapter, there wasn't like, we didn't consider one to be real and one to be imaginary, right? We just wrote them as a sum. Root 2 plus root 3 was the same as root 3 plus root 2, and it didn't matter how we wrote it. With complex numbers, the conjugate of a complex number is very specifically when we change the sign of the imaginary part. So even if I had written it as bj plus a, the conjugate would be negative bj plus a, right? You always switch the sign of the j part. So what's the conjugate of 3 minus 2j? 3 plus 2j. What's the conjugate of negative 2 plus 5j?
Negative 2 minus 5j.
Negative 2 minus 5j. What's the conjugate of 6j?
Negative 6j.
What's the conjugate of 3?
3.
3. There is no imaginary part. Or the imaginary part is 0, right? Now, I'm going to plot these numbers. So there's our real axis. Here's our imaginary. So this is j, 2j, 3j, 4j, 5j. The conjugate of a complex number has a nice geometric interpretation. So here's, I'm going to plot 3 minus 2j is right here. Its conjugate is 3 plus 2j. Right, so we just reflected it over the real axis. Negative 2 plus 5j is up here. Its reflection, its conjugate, is down here at negative 2 minus 5j. We had negative 6j. Oh, I should go a little further then, right? Oh no, we started with 6j up here, and then its conjugate was down here at negative 6j. Again, just flipping over the real axis. And now we have that same geometric interpretation when we consider the conjugate of 3. When I reflect 3 about the real axis, it stays where it is because it's on the real axis. It doesn't move anywhere. Questions? Yes.
I might just be remembering wrong, but this used to be I instead of J for imaginary.
Yeah, like in mathematicians still call it I. Most math books will call it I. In applied math or engineering books, they call it J because little I is used as the variable current. And complex numbers show up all over the place in electrical engineering. Yeah.
Presuming we have class next week, assuming the quiz is going to be on this,
Yeah, it'll be like complex number stuff.
if it is remotely, how are we doing quizzes?
I'll address that in an announcement. Like, it'll probably be like maybe an assignment or something that you could submit.
Group quiz? Group quiz?
You're not supposed to get together. That's the whole point of like closing campus. If there's amid a virus scare, is that you don't all gather in the same place. Yeah. So I think you missed this, Alex. But if they close the campus, that's why I handed out 2. If they close the campus, we could still just have class on Zoom and we could do like assignments or something. You know, I don't think it'll be that hard for us to do it. If you are in a position where it's difficult, maybe where you live, you don't have good internet access or something, let me know. I'll still be recording and posting those recordings, so maybe that'll be a possible solution.
So for the kids that live in the dorms, I'm assuming they're going to get sent home.
I don't know.
I don't think so.
I don't know. They'll address that in an announcement if they decide to
What
close
did
the
Leslie say
campus.
yesterday that most colleges would try to keep the dorms open?
They are trying. Yeah, I mean,
Kind of makes no sense if you
But they
think about
said
it.
that
Like,
if you can stay home, stay home.
yeah.
Yeah, it's just like the
like
actual
the,
class.
oh, you can't afford to live at home, so stay in the disease area.
Well, the idea is just to not spread out, I think, right? Like, okay, that's all I want to get through today. So I will take your questions on the last chapter. Radicals, multiplying, dividing, adding, subtracting, solving an equation.
Can we go over 3 in the practice quiz?
Mm-hmm. Oh, yeah, that was a good one. Okay. So that was like more involved. I looked at it, I was like, oh, that looks good. And I was like, oh, wow, there's a lot to do here. So, you know, I think everybody starts the same way, right? Like, we're going to split up those radicals over division. And then I always, like, if possible, before I do anything else, I simplify radicals. The 14x 21y fraction, like, there's nothing we could do with those. But we could take out factors from the second fraction. So that's how I started out. Then we have 2 things to do. We need to rationalize the denominators, and we need to combine get a common denominator. So I started by rationalizing the denominators. So that's what I did here. When you do that, if you look at this one, the first fraction, 14x 21y, 14 is 7 times 2, and 21 is 7 times 3. So I have a 7 squared, 2, and a 3. So once I did that multiplication, I was able to simplify this radical. So I took that out. And that's all over 21y. Multiply this one by 2x on the top and the bottom, but that doesn't lead me to anything that I can simplify, right? So then we're over here. This fraction, turns out we could reduce, and I did that first. If you wait to reduce later, fine, like it'll work, okay. No?
I know it worked, it was just annoying.
Okay. It'll work. You'll be annoyed. That's fine. So so this is root 6 xy over 3y after we cancel those the 7s. And here's we have 3 root 6 xy over 4x. Now I can focus on getting a common denominator. So I hit the 4x on the top and the bottom here, the 3y on the top and the bottom here. And our common denominator is 12xy. And then we have this sum. And then the last thing that you want to observe is that these radicals are the same, 6xy, 6xy. So you want to combine them, which when your coefficients are not just constants, really when combining like terms to simplify a radical is like saying, I'm going to factor out a radical 6xy. And then what do I have left inside? That's 4x plus 9y. Other questions?
So that's not on the quiz, right?
Well, wouldn't you want it to be since we just talked about how to do it?
Kind of.
Okay, well, it sounds like maybe